Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Welcome back to Reliability Matters. I'm so glad you're here. It's been a little while since we've talked about solder paste, and there have been quite a bit of conversations and video interviews and technical articles about solder paste, in particular low temp solder paste. So I thought it would be a good idea to bring in my friend and my colleague, Tim Jensen from Indium Corporation. Welcome, Tim. Thanks for joining us today.
Thank you for having me.
Yeah, of course. Just for a little bit of background, you and I have known each other, off and on in the electronics industry, rubbing shoulders at trade shows and, probably having a beer or two after a show. And we both serve together on the SMTA board of directors. So I see a lot of you I've seen a lot of you over the last year, usually in this format. I don't know what you look like in real life anymore, but I've certainly memorized your digital profile. But thanks for being here. Let's talk about solder paste, shall we?
Absolutely.
So
the best topic there is, right?
Best topic there is if you're a solder paste person, right? So I did a little bit of research on solder paste selection. I mean, I know about solder paste. I don't know what you know about solder paste, but I know enough, because our job in the cleaning world is to remove the residues your stuff leaves on a board, or doesn't. It depends on the type of paste. But from what I understand, in a real simplistic world, there's basically three things that one looks for in solder paste, or at least three of the considerations. One would be the alloy type, one would be the flux type, and then any special characteristics. Now, I know that's just probably the press box 36,000 foot view. There's probably a lot more details in the minutia of solder paste selection. So let's go over what the processes are for solder paste selection. Tell me about alloys first. What are the different types of alloys, and maybe what would drive someone to select one alloy over another?
Yeah, absolutely. As you mentioned, kind of when you look back at solder paste, the basic construction is a mixture of a flux and a metal powder. And so as you stated, the very first thing you got to think about is what alloy or metal powder are you going to use? And there's a number of different characteristics that you might use for determining that. But generally speaking, it's either a melting point requirement, an environmental requirement, or a mechanical reliability requirement. And so those are generally the three things that the people are looking at when they're trying to select the appropriate alloy. And so if you look at kind of the mass of electronics that are built today, most of them are using lead-free solder, what is often referred to as SAC 305, which is tin, silver, copper alloy. And I would say that's the de facto standard that people would be using. And so, that would be where people would start with from a material perspective. That has a melting point of about 217 degrees C. And so generally speaking, when you talk about the alloy, you want the use condition to be 30 to 50 degrees below the melting point of that solder at least. So that's one characteristic is, okay, when I'm using this product, is it ever going to approach something that's within 30 degrees of the melting point of the solder? If so, you probably want to select something higher in melting point. And then the next thing is looking at kind of the mechanical reliability attributes. And so certainly, because this tin, silver, copper alloy is used quite commonly throughout the electronics industry, I would say its base level of reliability is pretty good for the majority of applications. However, there are certain niche applications where it's actually not the ideal choice. So, for example, one case might be under the hood applications for automotive, where the temperature gets quite high. So you're talking temperatures often at sustained time periods above 150 degrees C, for example. Well, in that case, the tin, silver, copper alloys start to degrade with time, and so over time they become less mechanically reliable. And so in those cases, you want to look at an alloy that perhaps has either a higher melting point or improved mechanical reliability attributes. In another case, another example would be for very small solder joints that are subject to a lot of mechanical shock. So again, tin, silver, copper tends to be somewhat of a rigid alloy, and so on mechanical shock, you can get some brittle type fractures with it, especially on high impact type situations. And so those are a couple of scenarios where you might want to choose a different alloy that more adequately suits your specific needs. So I would say first looking at the melting point requirements, and then second looking at the mechanical or physical reliability requirements of your specific application.
Yeah, that makes a lot of sense. Particularly, we don't want the board to reflow in use, and we don't want the components to fall off due to shock in use. So that makes a lot of sense. What about a flux selection type? Obviously there's. I look at the world, and I'm in the cleaning business, as you know. So I look in the world as clean or dirty, right? So I see water soluble fluxes, rosin RMA type fluxes, ROLO fluxes as dirty, and you used to see all the no cleans as clean. And although I look at things differently today, not that the no cleans are dirty, but if the no cleans are completely clean, we don't clean anything off the board, and then therefore there are other dirty things on the board. So we're always coming up with a justification to clean. But what are the motivating factors? What should one consider when they've already checked off the right alloy now? Now they have to look at flux species. I know clean and no clean would be very common drivers, probably the most common driver, but touch on what are some of the other factors that one might consider when they are selecting a flux.
Yeah, as you said, that type of end process, how you're going to use the flux, and whether you plan to remove the flux residues or leave the residues on. Like as you stated, no clean doesn't mean no residue. It means a residue that's relatively benign and in many cases is not going to cause any electrical reliability type of issues. However, when you start looking at high reliability applications, you're going to want to clean off that residue regardless. And so you want to select a flux that's appropriate for that processing condition. And then secondarily, you want to select a flux that's appropriate for cleaning off the oxides in your specific scenario. So there's two things to look at relative to oxides. There's the oxides from the metal powder that's mixed in there. So for example, if that's the SAC alloy, you have to clean off those oxides so that during reflow, all those particles wet together and coalesce into one uniform solder joint. But you also have to clean off the oxides on the surfaces of the areas to be soldered. The solder is only going to wet to those metallizations if they're oxide free, so that the wetting can occur. And so looking at those scenarios, you select a flux that's appropriate for that soldering type condition. So certain oxides are more tenacious, more difficult to remove. You may need a more aggressive flux to remove those oxides. And we can help obviously decide the appropriate flux for that. And then I would say the third attribute is the physical use of the material. So for example, in many cases, people are going to stencil print the solder paste onto a printed circuit board. Well, the stencil printing process requires a flux that has a very specific rheology that allows it to fill the apertures, release from those apertures. That flux may totally be inappropriate if you're doing some type of dispensing or jetting application. And so the process in which you're applying the material also dictates what flux is appropriate. And so I would say kind of those three scenarios. The end disposition of that flux. Are you going to clean off the residue or not? The oxides that you're removing, how tenacious are they? How difficult are they to remove? And then how are you applying that solder paste, via printing, dispensing, jetting, or some other methodology? Those are kind of the three factors that you would look at for trying to determine the most appropriate flux.
Oh, excellent. Talk to me about low temperature solder. I'm hearing more talk and reading more articles about low temperature. I'm seeing, it may have been you or someone else on a panel recently even talking about it, but what are some of the advantages of low temperature solder, and how much lower a temperature are lower temperature solders?
Yeah, there's a couple of really exciting and interesting attributes of lower temperature solders that have drawn a significant amount of interest. And so I'll get to the different melting points in a moment, but just in a kind of holistic picture, as you reduce the melting point of the solder, you then can reduce the thermal excursion that you're going through to reflow it. So if you can reflow at a lower temperature, you can often use lower cost materials for your PCB, your components. So you have a potential cost advantage. Secondarily, at a lower reflow temperature, you're generally going to have less deformation of the material. So one issue, for example, is warping of components and boards, and that can create different defects like we call head and pillow or non-wet open type defects. So lower reflow temperatures results in less warping or deformation of the surfaces that you're soldering, so that can improve the process yield. And then third, low temperature solders potentially enable you to do secondary assembly on a circuit board that already has traditional SAC solder on there. So for example, you built a circuit board and you want to put on some type of RF shield afterwards. Well, you don't want to use the same melting point solder there, or the entire circuit board will reflow again. So a lower temperature solder can potentially enable you to do additional assemblies on that circuit board without dramatically affecting the rest of the solder joints that are already built on there. And to your point of, well, how much lower is it? There's a lot of different options depending on the application, and there's no perfect scenario. Generally speaking, these alloys often contain either the metal indium or the metal bismuth, and as you reduce the melting point, you can obviously reduce the thermal excursion that you're going through from a reflow perspective, but they often have downsides from a reliability perspective. For example, bismuth tends to be quite brittle, so that means that you have limitations relative to what type of scenario that product's going to be used in. If you talk about indium forms a intermetallic with tin that's very low melting point at about 118 degrees C. So while maybe that's acceptable in certain situations, if the melting point's 118 degrees C, you probably want to be in an application that's no higher than 80 degrees C from an operation perspective. So it limits the upside on some of your operating conditions. And then we have some alloys that are what we'll call slightly lower than SAC reflow temperatures. And so these are alloys that are similar to tin, silver, copper, but give you a little bit more process window. So for example, an alloy might melt at 200 to 210 degrees C. So it's not what I would call truly a low temperature alloy, but it's slightly lower than the tin, silver, copper alloys, gives you potentially a slightly wider process window relative to reducing the peak temperature that you're undergoing from a reflow perspective.
Yeah, that makes sense. So when someone is selecting solder paste, alloys, flux, temperature, all that, there are drivers on the board design that would that would steer someone toward one selection or another. There are also on many SMT assemblies a variety of different types of parts on there. You've got these bottom terminated components and QFNs that probably require special paste characteristics, and then you've got connectors, and you've got other, maybe high mass soldering pads or leads that might on their own draw another conclusion to the paste selection. Generally, I think one would prefer to minimize the number of thermal excursions a board goes through a reflow oven. So is it acceptable, is it normal practice to have one paste selection based upon one specific criteria that doesn't necessarily match or is unneeded for the rest of the board? Does that make sense? How much do we pull to one side on our selection at the expense of the other side for other types of components? Who wins in this battle?
Yeah, we see this a lot when there's a very specific defect that's causing an issue on a line. So, for example, you talked about the bottom terminated components, and so they go, "Oh, we're getting low yields because we're having 50% voiding. So we need something that solves the voiding issue there." And as you said, you can select something that dramatically reduces the voiding in that scenario, but does it have the balance of attributes that are not creating issues elsewhere? And this is really the delicate balance of solder paste evaluations, is really to look at the balance of attributes, and no one solder paste anywhere is going to be the best at every attribute, right? And so it's looking at, well, which attributes are most important for me, and then balancing out the other attributes. And as you said, sometimes people make rash decisions based on the defect of the day that they're facing, but it can cause consequences down the line. And so we've seen cases where, we solved the QFN voiding issue, for example, but now our stencil life is terrible. We're replacing the solder paste a lot. We're getting print-related defects, things like that. So you've just shifted the problem to somewhere else, and then you start another evaluation to find the best printing solder paste, right? And then you switch back to the old paste, right? So it's really finding that balance of attributes. And again, I doubt there'll ever be the one product that is best across the board for every attribute you can possibly imagine.
Right. That's why Indium and other manufacturers of solder paste stay in business. That's why you have a large portfolio of products, right? Rather than, super paste. There's no such thing as super paste, right? That'll keep your engineers busy and chemists busy for years to come. Let's talk about, now that we've selected our solder paste and with its proper alloy and flux and special characteristics, let's talk a little bit about in-use information like handling. What are best practices for solder paste handling? And when I say handling, I'm talking storage, I'm talking use, not so much selection of materials, but the actual use of solder paste. What are some of the best practices?
Yeah, this is a common question that we get a lot, and there's not a single perfect answer for every product. Some products will vary slightly, but in general, one of the most important things that I try to stress to people is that solder paste is actually quite thermally stable. So what that means is that if you leave it out for 12 hours, 24 hours, it's not like the material instantaneously goes bad. It's not like some of these epoxy materials that cure at room temperature or things like that, where it'll instantly become bad. So one of the things that I really try to stress is, within reasonable limits, solder paste is really quite stable. And so that what I use that is to say, all right, if you're going to store it for a long time, store it in the refrigerator. But under short time periods, I would say of a month or less, storing it at room temperature is perfectly acceptable. really the only downside that happens at room temperature storage is over time you'll get what we call flux separation. The metal powder is a lot more dense than the flux portion. So that means that over time, the powder actually sinks to the bottom and the flux rises to the top. So you get a kind of a non-homogeneous material. This is not a complete failure of the material. You can actually stir it back and bring it back to homogeneity. But it does create some risks. Different people will stir at different conditions, and so storing in refrigeration prevents that separation from happening. And so it's a good practice for long-term storage to store it in a refrigerator. But if once you open a jar of solder paste, there's no need to worry about, all right, put it back in the jar, quick, get it back in the refrigerator, because that transfer back and forth in and out of the refrigerator causes its own issues. You get moisture condensation, things like that that can happen. Plus, you lose track of how old is that solder paste. You start mixing different jars into one reclaimed jar, and nobody really understands how long that paste has been around. And so I try to keep things as simple as possible. Once you open it, leave it out at room temperature. If you're not going to use it for more than a month, you're probably at a situation where you should just scrap the material. It's a safer option than trying to bring it back and forth between the refrigerator and not.
Yeah, that makes a lot of sense. We talked earlier about when we were talking about paste selection. We talked a little bit about in-use environment, whether it was going to be exposed to shock and vibration or high temperatures. Are there other in-use environmental considerations besides the temperature and the amount of shock and vibration that would drive someone to choose one type of paste over another?
Yeah, certainly. I would say the three big reliability terms are mechanical reliability. Is the solder joint reliable enough for the situation that it's in? Is it a cell phone? Is it a engine control unit in a vehicle? Is it something that's in a harsh environment and out in the environment? So that mechanical reliability is one thing, and that's something that you can understand from doing different types of thermal cycling, things like that, to stress the solder and assess how reliable it's going to be for a variety of different situations. The second would be electrical reliability, and this is really primarily the residues that are on the board, and this comes down to when you solder, you have basically a mixture that's 50% metal and 50% flux by volume. So after you reflow it, you have all this residue left behind. Now, in many situations, that residue may be perfectly acceptable to leave on the board, and that doesn't mean that there is no residue. One of the things that sometimes people confuse is no clean doesn't mean no residue. It means that you're intentionally leaving contamination on the board, and you think it's good enough for that specific application. But as we know, as you go into higher reliability applications, maybe very high frequency RF type applications, the residue can have an impact on that overall assembly. And so, therefore, do you clean it off, and how do you clean it off? That will come back to, well, what flux do you use for the process? And then the third bucket of reliabilities is thermal reliability, and this is how efficiently does the solder dissipate the heat. And this is typically not an issue for small solder joints, like for capacitors and resistors and things like that, but actually larger solder joints like the ground pad underneath a QFN. The primary purpose of that is to dissipate heat from the component itself. And so designing that so that it's appropriate to dissipate the right amount of heat so that that component can last as long as possible is a very important consideration.
When you talk about no clean, someone said this to me once at a conference, and it just made a lot of sense. In the earlier days of no clean, whenever I talked about cleaning no clean at a live event, I'd always get the angry solder paste people, in the audience, objecting, just totally offended by the suggestion that we should clean no clean. After all, they put thousands of engineering hours into coming up with this, miracle flux that didn't have to be cleaned, and we're promoting cleaning it. But that's changed for reasons you've just stated over the years. There are applications where even the small amount of residue, which is benign in most applications, or is not benign, relative to frequency distortion and whatever. So there was one solder paste person that said, no clean doesn't mean don't clean. No clean is the species of flux that you would use if you were to make a decision not to clean it. You wouldn't use an OA flux. You wouldn't use, in most cases, an RMA flux. But if you're not going to clean, you must use no clean. It doesn't mean don't clean. It just means it's a species. It's a selection type. And that made a lot of sense to me. And a lot of flux manufacturers, again, would get offended because they would think that I'm impugning no clean, and I'm not. And I'm the first to admit in almost all applications, not all, but in almost all applications, the residue left behind from the no clean flux is benign. It is not harmful electrically or ionically. The big issue whether to clean or not is really what else is on the board. And when we cleaned, back in the days when cleaning was just a standard protocol, one of the many steps in the assembly process, when we removed the flux, we removed all the other, what I like to call usual suspects, the board fab contamination and component fab contamination and dirty little humans and things like that. And when we stopped targeting the flux because the flux became relatively safe and inert, we left all the other things on the board. And it's the totality of all those things that become problematic, not just the flux. So the cleaning business is still friendly with the no clean business. We're not competitors at all. It's a bigger picture beyond just the flux residue. There's everything else on the board. One of my favorite topics is mistakes customers make, stupid people tricks. And what are some of the common mistakes that you've seen as a solder paste person that people make when storing, using whatever solder paste? You must have a time when you and your service support engineers, kick back and compare horror stories, right? So what are some of those common mistakes that you see people make in general?
Yeah, I think that one of the biggest things that is so clear to me now that I've been in this industry for a while is that people generally don't spend enough time developing and optimizing the stencil printing process. And so if you think about the SMT process, the very first step is the stencil printing process where you're putting the solder paste onto the board. And typically any studies that you see out there, they say 60 to 75% of all defects can be attributed back to that stencil printing process. And what's great about the stencil printing process is if you identify a defect right after printing it, it costs you almost nothing to repair it. You can wash the solder paste off that board and oftentimes reuse that board and reprint the solder paste on it. Each step you go down the SMT process line, the more it costs you before you identify that defect. And so, yeah, it's important at the end of the line after it's reflowed to inspect it. But the amount of cost to repair a circuit board that's fully assembled and fully reflowed is monumentally more than identifying the print defect at the beginning of the process line and simply cleaning the board. Or even if you scrapped it, you're only scrapping the PCB itself. You're not scrapping all the expensive components that go along with it. And so we really try to emphasize the importance of the stencil printing process. And that actually goes back to your comment about cleaning the no cleans. The reason that people are so focused on using no cleans, even though they're cleaning, is because the stencil printing process. A no clean material is very resistant to moisture absorption. And so that means that they're very robust for very long stencil lives. You get very consistent printing, and therefore you get much higher yields at the end of the process. Now, the residue itself generally cannot be cleaned with just pure DI water. So you need some type of solution to remove the rosin constituents within that residue. So you're putting a little bit more stress in the cleaning process and a little bit more time to improve that. But the benefits you get from a very high process yield with a very robust stencil printing process dramatically outweighs any additional costs that you would have for that cleaning process.
That makes a lot of sense. How's miniaturization changed the solder paste business? It's so hard to fathom how small components have gotten over the years. You can barely see them. In one of my slides for my technical presentations, I show a dime, a U.S. dime, and there is a component within the nose of the president, on the dime. Right? I just can't understand the technology for even placing those components, much less reflowing them. So, how has that kept you guys on your game as components get smaller and as the soldered areas, the pad and the lead, become almost microscopic in size?
Yeah, it's actually created some complex challenges, and so one, when you look at these very small components, you know what? If you spent all your time, you could design something that printed and reflowed really well for those small components. But the reality of the situation is you have a mix of those really small components next to some larger QFNs or other things on the circuit board. And so you need something that not only is effective for those very small deposits, but also reflows and prints robustly for that broad spectrum of components on the board. And so it's, again, I think it's that balance of trying to identify the attributes that give you the widest process window across the entire assembly. From the miniaturization, a lot of the focus is around the powder size of the metal powder. And so obviously, as you go to smaller and smaller openings in your stencil aperture, you need to go to finer diameter powder to adequately fill those apertures and release effectively. And so from a fundamental perspective, it's forced us to really focus on finer powder technology. What the kind of the de facto standard of the early 2000s was what we called type 3 powder, which was powder that was about 25 to 45 microns in diameter. And as probably in the 2010s, type 4 became the de facto, which is 20 to 38 microns, so a little bit smaller powder. Now, for a lot of the assemblies, we're talking about type 5, type 6, type 7, even type 8 powders, which are in the 2 to 5 micron particle size, which creates challenges, one, manufacturing that robustly, but also, if you think about solder powder, you have the surface of that powder, which can become oxidized. The smaller those particles are, the more overall surface area you have to become oxidized. So oxide becomes a very significant challenge as you reduce the powder size. And so you have to look at a flux that's effectively removing those oxides. And an easy way to do that is to make the flux more aggressive, but then you start to fail on other things like electrical reliability requirements. And so there's, again, this balancing act of, can we make it reflow robustly enough? What can we do in the reflow process to make the yields more robust? and how can we balance all those other attributes that are also still really important from a customer's perspective.
So if the smaller the mesh, the smaller the sphere size, the type 8, for example, the extreme, because it is more subjective, more influenced by oxidation, more easily oxidized, does that mean that a type 8 is not compatible with a no-clean flux? Because no-cleans are the kind of the least aggressive in terms of controlling oxides, from what I understand. Maybe that's changed. So can you still get a type 8 in a no-clean footprint?
Yeah, I would say yes, but you're absolutely right. The let's just say the no clean that you use for type 3 may not be appropriate for the type 8. And secondarily, you may need to make other sacrifices in your process. For example, maybe you have to reflow in nitrogen to get effective coalescence. And so again, it's this balancing act of what other sacrifices are you willing to make,
sure,
to get the process yields to where you want it to be. But absolutely agree that all things being considered, the coalescence of type 8 is going to be much poorer than the coalescence of type 3, for example.
You better have clean boards, clean components, nitrogen environment, all those things. That kind of brings me back to the early days of no clean, the very early days of no clean, in the early 90s, late 80s, when the Montreal Protocol was announced and the rush to no clean. I remember there was multi-core, I think, their X32 or something. That's one of the earlier ones I remember. And, you basically had to use some kind of inert atmosphere in your oven back then, because no cleans were exceptionally weak in terms of oxidation protection back then. Everything needed to be fresh and clean and ready to, and very solderable back then. And slowly over the years, I saw almost the requirement for nitrogen inertia in an oven, and even in some wave soldering machines, kind of went away because it just became not that big a deal anymore. But I think the early days of no clean remind me of what we're saying about the smaller the mesh size. The type 8 reminds me of the early days of no clean, where everything needs to be in order, right, in order for a successful reflow process to occur.
Yeah, and we've kind of gone through some waves, like you said, the early days of no clean, and then the advent of lead free. People were very concerned about the reflow characteristics. When you look at tin lead solder, people use tin lead because, man, it works really good.
Sure.
It solders well. It's easy to use.
Nice and shiny. It looks good.
Yeah. Go into a SAC reflow, all of a sudden there's all these things. You have a higher temperature. You have all these other attributes that you have to worry about. And so there was this kind of pushback towards more nitrogen use to try to lessen the difference between that transition. And then as the technology's improved, and it's not just the flux technology, but also the powder technology, how we make it, how we ensure that it remains oxide free prior to mixing it together. It's that combination of technologies that has enabled us to kind of now, in, I would say, typical lead-free assemblies, most of them are in air reflow again. But now as we push towards very small particles, there's this reemergence of nitrogen atmospheres to try to, again, make the process more robust.
Yeah. I almost hate to bring this up because this subject has been beaten to death on this show and many others, but I can't have a solder paste expert on the show without at least asking about voiding. Is the industry no longer as concerned about voiding as they used to be? Have they settled on a acceptable voiding percentage? I've talked to other experts in the reflow area and the X-ray area, and I've heard a lot of people, maybe not quite as strongly as I'm going to paraphrase it, but basically say, yeah, it's all overrated. Voiding's fine. That you don't need 100% coverage. 70% is fine. I heard someone say 30% of coverage. 70% voiding is even fine in most cases. So, have we, as an industry, as a solder paste industry, have we pretty much settled the whole voiding concern? And If not, if there are legitimate concerns for voiding, have we reduced the amount of voiding through engineering?
Yeah, I would say the concern is still there. Whether or not it's justified concern, I think is still very much open for debate, as you talked about. I think there are certain scenarios where it does make a difference. And for example, we brought up the QFNs, the large thermal ground pads underneath. Those have an impact on the thermal performance or the heat dissipation capable of it. And so that's something that you can define. But from a mechanical reliability perspective, in my opinion, it's very rare that the voiding is the leading contributor to a mechanical reliability failure. But the thing that makes it a little bit difficult to rule out completely is that the location of the void actually matters. So if you have, let's just say you have 20% voiding in your solder joint, but it's all at the very top interface where kind of is the narrowest or the necking point of the solder joint, that's where the most stress is going to be. And yes, that voiding could accelerate the crack propagation. And so when you look at an X-ray, you can't really tell where the void is. You know that it's there, but physically, is it at the top or the bottom or in the middle? If it's in the bulk of the solder, I would say almost never is it even possible for it to be a mechanical reliability issue. So in some cases, thermal is possible that it's a thermal or heat dissipation concern, and theoretically, if the void's in the wrong place, either at the very top or very bottom, depending on kind of the shape of the solder joint, theoretically it could reduce the overall reliability. But in general, yeah, I would still say voiding is overrated. And if we look back to, let's just say back to the 90s, before anybody had X-rays, nobody talked about voiding. As soon as the first X-ray machine came out, all of a sudden voiding became something because they could see it.
Yeah, I've long said it's a proven fact that X-rays cause voiding, because we didn't have a voiding problem before that, to your point. What's the most common solder paste used today in terms of alloy and flux composition and mesh size? What's your kind of flying off the shelf model?
Yeah, I would say certainly from an alloy perspective, it's SAC 305, which is tin silver copper with 3% silver. That's kind of the de facto standard lead-free solder today that's used in the widest variety of assemblies. And those are, generally speaking, the highest volume assemblies, talking about computers, cell phones, kind of consumer type products which use a lot of the solder. And generally speaking, those are all no clean type processes. So it's from a volume perspective, those are going to dominate the overall usage of solder paste.
Yeah, that makes sense. As we're getting close to wrapping up, let's talk a little bit about micro-dispensing and jetting. This technology's been around for a little while. When I first heard of these devices, I thought that was going to be a revolutionary technology. There's two types of new technology that we have in our industry or any industry. There's revolutionary technology, which is something that has never been done before. And then there's evolutionary technology, which is just something smaller, faster, cheaper, better than what we've already had in the past. I kind of thought that jetting and micro-dispensing would be revolutionary, but from my perspective, again, I'm not in that industry, but from my perspective, I haven't seen it explode. There's only, from my understanding, a handful of pastes that are suitable for that type of technology, and it just has. I don't think the printer people are losing any sleep right now, as I thought they might when the technology first came on the scene. So what's your take on jetting and micro-dispensing, and what are the pros and cons from a solder paste manufacturer's perspective?
Yeah, I think the concept of a jetting or micro-dispensing process and kind of the allure behind it is you have the ultimate flexibility, right? You're not constrained by stencils. You're not constrained by any geometries of the board. You can do things that are, non-flat surfaces, put solder paste into cavities, things like that allow you kind of more three-dimensional flexibility in your circuit board. So conceptually, that is certainly quite alluring. But the reality of the situation is still the vast majority of assemblies are going to be relatively flat PCBs, and no matter how fast your jetting equipment is, it's never going to be able to put thousands of deposits down onto a circuit board in a matter of 1 to 2 seconds, like you can with a stencil printing process. So speed is so much faster with a printing process, and so I think you'll never overcome that with, at least where we are today, with kind of the jetting or micro dispensing technology. And so the other aspect is relative to material cost and material performance. You're talking about, generally speaking, finer powder solder paste, which are going to be a bit more expensive, in small syringes, which are more expensive to package than jars or cartridges. So you have a significantly more expensive product. And yes, you can put it down onto a circuit board, without the requirement of a stencil. But frankly, the cost and lead time for stencils are so cheap that many places you can get a new stencil, within a day. And so, yes, there's a little bit of time lag to create a new stencil, but the cost is relatively low. So you still have a lot of flexibility to create new stencils and change stencils. I think the place where there is still some interest and viability is either post-assembly. So let's say secondary assembly onto a circuit board. If you already have components on a circuit board, you can't stencil print on it because you don't have a flat surface. So this allows you to come in and apply solder into different locations. This could be very applicable with the low melting point solders, as well as using it in places where potentially you have a cavity in your circuit board. So use the stencil printing for the large portion of the PCB, but then come in and jet or dispense into that cavity to either add or put the solder volume in those locations. So it can be an add-on and add some flexibility, but I don't see that it's going to be a widespread replacement to the stencil printing process.
Yeah, I agree. I recently interviewed on this show one of the founders of Nano Dimension. They are they combine 3D printing and inkjet technology to basically print circuit boards. It's pretty cool. They have a dielectric ink and a conductive ink, silver ink, and they just like an inkjet printer, go over the surface thousands of times and build up a board. And one of their claimed advantages is, we're no longer boxed into a flat surface for a board. Right now we're taking flat boards and putting them in round objects, and now they can actually print a board that is arc shaped or angular and things like that, which sound really good from a packaging perspective. But then, how do you print it? You can't print a L-shaped board in a stencil printer, right? So I think as that technology scales up and people are able to print custom-shaped assemblies, or boards rather, for their end-use product, that will certainly benefit from the micro-dispensing and jetting, because they can basically print, exactly where they want the paste to go, and then rotate the board and print more, and then rotate the board and print more, or have it done robotically so the board can stay in one place and the jet arm can go wherever it needs to go. So I see that as a very fringe technology that has some potential for very custom technology, and I don't think it's going to go away. I think it's probably going to increase, but of course, flat is efficient, right? So if we can keep things flat and planar, then we can get volume, and volume usually also gives us a much lower price. So
yeah, and there's competing technologies to making that round or non-flat surface, right? You could also think about, well, let's apply everything to a flexible circuit and then bend it, right? Or
yep.
one of the cool things that we work on at Indium Corporation is gallium-based liquid metals, and so these are liquid at room temperature. They're electrically conductive, and so if you have a fluid, therefore you have total flexibility of the substrate, and you can still conduct electricity through it. And so there are some cool other approaches to addressing that flexibility or non-flat surfaces. And so I do think kind of that jetting micro-dispensing plays a role in broadening those types of scenarios that we could potentially enable solder to be used in.
You talk about liquid at room temperature. I remember way back in high school, 1,000 years ago, in science class, the teacher wanted to show us mercury. And the way he showed us mercury is he had one student hold their hands out like this, and he poured the mercury into that person's hand, and and that person would then pour it into someone else's hand, and it went around the room as a liquid in the air sample, right, that we're handling. And I don't think the dangers of mercury poisoning were really fully understood, back in 1974, when this happened. But that was and then I remember someone dropped it, and of course it just scattered into a million tiny little balls. But that was my experience with liquid metal, right? That was very interesting, and looking back, probably pretty stupid to do it that way.
Yeah. Actually, sorry, I was just going to say that, now most of those mercury applications have been replaced by gallium, but mercury still has some very phenomenal characteristics, other than the fact that it's quite hazardous to human life. It's very unique that it doesn't oxidize. And so unlike gallium forms an oxide film on the surface, which is something that you have to try to deal with, but mercury is quite unique in that. And so it is a very cool metal. Unfortunately, a bit too toxic for most applications.
Right. Well, I'm 60 now, so obviously if there are lasting effects, it hasn't hit me yet, but or maybe it hasn't. I just don't know. Let's wrap up with this. Besides the obvious cost, right? Besides the price of solder paste, how does one choose a solder paste supplier? There's a lot of solder paste suppliers out there. I'm sure all make good products, and some may have some specialties. I know Indium is known for certain types of products more than maybe others. But what's your recommendation to choose a company to work with besides price? I mean, I don't want to get into the commoditization of these materials. I think that's just a race to nowhere, right? It's a race to the bottom when people just put price in front of everything. So take price out of the equation. What's your advice to people besides pick up the phone and call Indium? What are some of the selection criteria? Yes, of course.
Yeah, I think that for sure the very first thing is to make sure that the supplier has the appropriate product for your application. Like you said, there's many different solder paste suppliers. All of them are making good products for a variety of different applications, but not every solder paste is right for every application. And so aligning kind of the overall needs, so understanding what specifically you need, whether it's a melting point requirement or reliability requirement, some type of different process like we talked about, jetting or very long stencil life, or maybe it has to be exposed to certain levels of humidity. So understanding your requirements and making sure it's a good match for the products that you're evaluating is certainly number one. And then looking at the supplier that can support your needs, and that could be from a technical perspective. Can they help address any ongoing technical needs to help you optimize your process, make sure that you get the highest yields possible? If there's an issue, do they have the quality practices in place to ensure that they resolve the issues effectively, and have kind of continuous improvement programs to ensure that those issues don't happen again in the future? And then I guess the third would be kind of global availability, making sure that support and supply is effectively available in the places where you're going to need it, whether you're building in the United States, Mexico, China, Vietnam, wherever it may be. Make sure that supplier can support all of those locations effectively, again, from a material perspective, from a quality perspective, as well as a technical support perspective.
Well, that's very good advice. Tim Jensen, thank you so much for agreeing to be my guest today. I really appreciate all your wisdom and knowledge and advice. And thanks for being here.
My pleasure. Thank you for inviting me.
Of course. Thanks for listening or watching the Reliability Matters podcast. Be sure to subscribe to the podcast on your favorite podcast app, such as Apple Podcasts, Google Podcasts, Spotify, and so many more. Also, be sure to check out my other podcasts, including the Concept to Creation podcast, where I feature conversations with entrepreneurs within the electronic assembly space, and the Innovations in Technology podcast, where we discuss innovative products within our industry. All three shows are also available in video format. Check out the Reliability Matters or Concept to Creation or Innovations in Technology podcasts on YouTube. Just search the show's name and you can find all three shows. Or go to MikeConrad.com. That's Conrad with a K. All three shows also appear there. Again, thanks for being part of my podcast family. I appreciate you being here. Until next time, stay safe, stay healthy, and stay happy. And of course, keep doing it right. See you again soon.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.